Okay, as I said, no right or wrong answer here. So nice range. We've got everything from 11 to up to 15. Okay, excellent. So that's good. We've got a nice range there. So what I'm going to do is just go switch my screens, and we'll have a little look at how we can demonstrate this on GeoGebra. So just bear with me whilst I switch my screen. And it's not coming up for some reason, so I'm just going to show my desktop instead. There we go. Okay, so hopefully you can see that. So let's have a look then at the probability. So some people say 11. So the probability that we flip a coin 20 times and get 11 or more heads is about 41%. So I'd say 41%, I'm not that suspicious. I expect 10, but it's not guaranteed to be 10. I'm not too surprised if I get 11. If we up it to 12 or more, then we've got 25%. So a lower probability, but probably not enough reasons to be suspicious at that point. Then we get into 13, and we get to about 13%. So this is where you start to maybe have your doubts. But I would still say 13% generally isn't, it's unlikely, but it's not highly unlikely. Then we get to 14, and this might be the point where you start to get suspicious. The probability of getting 14 or more is 5.77%. So you can just see this number here. Okay, it's just adding up the probability of 14, 15, 16, all these blue bars here. This is now getting to the point where we would start to doubt if this coin's fair. But it depends on how confident you want to be to make that statement that this coin is biased. Now, some people might say they want to only be wrong 5% of the time. Some people might want to be wrong only 10% of the time. That is where our significance level comes into. So you might say 14, it's unlikely, but it's still not below 5%. So then if you go to 15 or more, then we get to 2%. Some people might be really rigorous before they make the claim that the coin's biased, and then say 16 or more, which is just 0.5%. We can also go the other way. So a lot of people saying how many number of heads and thinking I'd get too many heads than I'm expecting. But remember, you could get a very small number of heads, meaning that you're getting a lot more tails, meaning that there's evidence suggests it's biased towards tails instead. So you could also test this lower tail here, and you can see because it's probability of 0.5, it's symmetrical. We get about 2% probability it's 5 or less. So just bear with me while I switch screens back again. And go back to OneNote. Okay, but if you've got any questions, there we go. Can you see? Just tell me you can see my window again. So you've got the flip the coin 20 times again. Okay, yes, okay, excellent. Right, so what we're going on today then is hypothesis testing for binomial distribution. So far we've done this with normal distribution, we've done it with product moment correlation coefficient, where we're testing to see if there is or isn't correlation between two sets of data. Now what we're doing is hypothesis testing for the binomial distribution. So a few things are different here. The main thing really is that we're working with discrete data rather than continuous like we were with normal, and with product moment correlation coefficient we had the critical values in the tables, and we don't have that for binomial. So first off, we're going to go into our first example. We just set up the hypothesis test, and there's a nice little flow chart in your booklets. I'm going to come back to that in the final lesson on hypothesis testing, just so we can kind of round it all together. So firstly, we've got Ryan wishes to test whether or not a coin shows bias. He decides to flip the coin 80 times and count the number of heads. Write down a suitable null hypothesis. So when we're writing down our hypotheses, so it's the same as what you were doing with normal, what you're doing product moment correlation coefficient. You write down H0 and H1 and this colon here. So H0 is the null hypothesis. Basically, that just says that there is no change. What we believe to be true in the beginning is still true. So if the coin, we start off by assuming that there is no bias with the coin, so the probability is just 0.5. So with normal distribution, for example, you'd write your mu there for mean. For binomial, we just write the probability equals whatever we believe it to be true in the beginning. The alternative hypothesis, so yet again we write P, and depending on whether it's a one-tailed or a two-tailed test, we're in our later examples we're only going to focus on one-tailed, but in this example, this would be a two-tailed test. So I'd write the probability does not equal 0.5. Okay, because here it says whether or not the coin shows bias. It doesn't say bias towards heads or bias towards tails. If it just said bias towards tails, I'd put the probabilities less than 0.5 of getting ahead. If it was biased towards heads, I put the probabilities greater than 0.5, but it just says whether or not it shows bias. So it doesn't say towards heads or tails. So it's a two-tailed test, which is why I put does not equal. So in words, what the null hypothesis is the probability of getting ahead is 0.5. The alternative hypothesis is that the probability of getting ahead is not 0.5. So that's our null and alternative hypothesis. And then for part C, describing the test statistic, basically this is just what you're measuring or what you're observing. So this is basically what X is. If you say X is binomially distributed with N as 80, P is 0.5, okay? X would just be, in this case, the number of heads after flipping the coin 80 times. Okay, so when it says test statistic, it just means what are you measuring, what data are you collecting, okay, what are you counting. Okay, in this case, we're just counting the number of heads when we flip the coin 80 times. So second example, so in these first two examples, we're just kind of setting up the hypothesis tests, and then we're going to do some actual calculations in a bit. So Barry, an electric candidate, believes he has the support of 85% of his residents in his town. A researcher wants to test at the 5% significance level whether Barry's overestimating his support. Okay, overestimating is the key word here. The researcher asked 20 people whether they support Barry or not. Only 4 say that they do. So write down 2 suitable hypotheses. So the null hypothesis is that Barry's correct, and the probability that people support him is 85%. Okay, so that is our null hypothesis. That's what we believe to be true in the beginning. Now the researcher thinks he's overestimating his support. So this would mean that the probability is less than 85%, okay? So he thinks that, you're going to get less than 85% of people supporting him because he's overestimated that support. So those are our hypotheses. It's important that we always write them first, especially when we go into the bits in a second. And then B, explain the condition under which the null hypothesis would be rejected. Okay, so what we're saying here is we asked 20 people, and if he has 85% of the support, you'd expect 17. But it might just be that your sample doesn't maybe have his biggest fans, and you find a sample with only 16 people that support him. I think if he says 85% of people support me and you find out 80% do, it's not that much reason to be suspicious. 15, you're going to lose 15, probably still okay. 14, you're probably starting to get in that area now where you're starting to get suspicious, and then so on. So where we would reject the null hypothesis, we reject the null hypothesis if the probability that 4 or less people support him in a sample of 20 is less than 0.5 when the data is binomially distributed. So we would reject the null hypothesis. So if we work out the probability that if the probability is 0.85, like he believes to be so, we'd reject the null hypothesis if the probability of 4 or less people supporting him is less than 0.5, okay, less than our significance level. Okay, if you work this out, actually, it's a very low probability. Okay, you can probably just, by looking at thinking, if someone says 85% of people support me and only 4 out of 20 do, really those numbers already kind of jump out to you as suspicious. If you actually work it out in your calculator, it's something like 10 to the minus 10. So definitely would be rejecting his Barry's claim here. Okay. We'll talk more about critical regions in Friday's lessons. If you work that out, you end up getting the critical region is 13 or less. Okay, so once you only have 13 people or less in the sample supporting him, that is less than 5%. So that's when you would reject your null hypothesis. But we'll talk more about our critical region in a future lesson. Okay, today in these examples, we're just going to focus on one-tailed tests. So if there's any questions, please pop them in the chat. I'll just do one quick check. I can't see anything there. So the next 3 questions are exam style questions, and what I'm really going to focus on here is making sure that you get the right notation, you get everything you need for these 6 marks here. So first, we've got past records from a large supermarket show that 20% of people, the go and highlight key things as I go along, 20% of people who buy chocolate bars buy the family size bar. On a particular day, a random sample of 30 people was taken from those that had bought chocolate bars, and 2 of them were found to have bought the family size bar. Test at the 5% significance level whether or not the proportion P of people who bought a family size bar of chocolate that day had decreased. State your hypotheses clearly. So the first thing we are going to do is write our hypotheses. Okay, it's really important that we do the step first. So the null hypothesis is just going from those past records that the probability is 0.2. Then the alternative hypothesis, so the claim here is the number of people that bought the family size bar that day had decreased. So we're only looking at change in one direction here. So it'd be the probability that it's less than 0.2. Also, what we should do is write down our distribution. So here, we're going to use X as our test statistic. Okay, X is just going to be the number of people that buy the family size bars out of the sample of 30. So X is binomially distributed with a sample size of 30 and a probability of 0.2. Now, when we do the hypothesis test, the probability for your null hypothesis will always be your probability for your distribution. Okay, so here, if you've got a probability of 0.2 for your null hypothesis, you put a probability of 0.2 in there. And the 30 just comes from the fact that when we're taking a sample, we're taking a sample of 30 people. Okay, let me know if you do have any questions about that. So we are looking at 2 of them buying the family size bar. So what we need to do, we don't just work out the probability of exactly 2. we have to work out the probability that 2 or less, because if we're rejecting it for 2, we're definitely rejecting it for 1 and 0 as well. So we need to write down the probability that x is less than or equal to 2. Now, what you want to bear in mind, we're only doing one tail test today. If your alternative hypothesis has a less than sign, when you're working out your probability, you should have a less than or equal to sign. Okay, and when we do an example in the next one where we've got a greater than sign, you should have a greater than or equal to sign when you're doing your probability. So we work out the probability that x is less than or equal to 2. So we just use our calculator here. Binomial CD, we put in x as 2, n as 30, p is 0.2, and we get 0.04418 when we do so. Now, I'll look at this probability, and what I now do is I compare it to my significance level, which is 5%. So the probability here of 2 or less is less than 5%. Now, if the probability is less than your significance level, we reject H0. Okay, the probability has fallen below 5%, which is enough reason to cause suspicion. Okay, so we then say reject H0. There is sufficient evidence. There's a variety of different ways you can write this. What I tend to do is always write there is sufficient evidence or there is insufficient evidence, depending on my conclusion. There is sufficient evidence to suggest the proportion of people, and this, what I'm doing now is just going back to the question and pretty much copying a lot of the context in the question. Okay, don't just say reject H0, sufficient evidence. Make sure that you do reference the context, so the actual scenario here. So in this case, you're talking about the family size bar, okay, or the proportion of people. Those are the key things that you need to mention in terms of that context. Okay, so just to recap there, put your hypotheses, write down your distribution, work out your probability based on your sample, and then compare that with the significance level, and then make a conclusion. Do you reject H0? Do you accept H0? Here, we've got enough evidence to suggest that the probability isn't 0.2. We would expect the probability is actually less than 0.2. Please let me know if you've got any questions in the chat, and then we'll have a look at example 2. Okay, unless I can see anything, I'm just going to go straight ahead into the second example. So the standard treatment for a particular disease has a 40% of success. A certain doctor has undertaken research in this area and has produced a drug which has been successful with 11 out of 20 patients. The doctor claims, sorry, the 40% is significant as well. The doctor claims that the new drug represents an improvement on the standard treatment. Test at the 5% significance level, the claim made by the doctor. Now, he's claiming that there has been an improvement on the standard treatment. So firstly, write your null hypothesis. Your null hypothesis is the probability that P equals 0.4. In the chat, just to check we're all okay with this, what would be my alternative hypothesis? Okay, excellent, James, Carl, Tilly, yeah, Laura. And the probability, Mia, Dominica, the probability would be greater than 0.4 because we're looking at an improvement. Okay, so if it's an improvement, we'd expect the probability of success to be greater than 0.4. So That's my hypothesis. Now write your distribution. So this is binomial distribution here. Okay, it meets all the 4 criteria we looked at last week. There's a fixed number of trials, fixed probability, probability of success or failure, and probabilities are independent. So n is going to be 20 because there's 20 in our sample, and the probability remains 0.4 when we do the distribution. Okay, we always use our null hypothesis probability. So then what I do is I find in my sample it's been successful with 11 out of 20 patients. Okay, so if the probability is 0.4, then out of 20 you'd expect 8. What we're going to see is it that significant to find that 11 or more have been successful here? So we do the probability that x is greater than or equal to 11. Remember, if I have a greater than here, I have a greater than or equal to sign here. Now, when I'm working out this, remember I'm using discrete data here. I'm looking at 11, 12, 13, all the way up to 20 successes. Now, on my calculator, it doesn't tell me going to the right here. It'll always tell me the probabilities going to the left. Okay, tell me that number and then less than. So if I put in x is 11 on my calculator in binomial CD, it would tell me 11, 10, 9, 8, 7, okay, which I don't want. So what I need to do is I do 1 minus the probability of x is less than or equal to 10. So that means take away all the probabilities that you don't want. So take away the 10, the 9, the 8, all the way to 0. So work that out on your calculator. Get 0.8725, and then do 1 minus that, and we get 1.275. So then what we would say, we compare that with our significance level. So this is greater than 5%. So whilst 12.75%, it's not unlikely enough to reject the null hypothesis. So what we do here is we accept H0 and then say there is insufficient evidence to suggest. So you can see I've almost got this like template every time I say accept or reject H0. There is sufficient evidence or insufficient evidence to suggest, and then I just go back to the question, read it again, and just put the context in. So the new drug represents an improvement. In terms of that claim, I mean, I've just pretty much kind of just copied that really and just put that there in my conclusion. Okay, if there's any questions, please put them in the chat, or you can always save them for later and ask us after the lesson if you've got an individual question. Right, I'm going to do something similar to what I did yesterday. I'm going to leave the third example. Okay, that is in the assignment notes. If anyone does want me to go through that, then do let me know. But I'll let you have a look at that one for yourself. See if Lorna gets thrown out of the casino or not. So have a little look at that one. I'm just going to go straight into the recap. And a couple of other things that I just need to mention. So just as a recap, what we're going to do with these problems. So when we look at one-tailed test day, Thursday, we'll look at two-tailed, and Friday we'll look at critical regions. So always write your hypotheses and your distribution. Okay, so your null hypothesis and your alternative hypothesis. Your null hypothesis will always be probability equals whatever it is, and your alternative hypothesis for the one-tailed test is just going to be greater than or less than that probability. Work out your probability based on your sample, and then compare that probability with your significance level. And remember, when you work out your probability, if you find there's 2 in your sample and your alternative hypothesis has a less than sign, then you do less than or equal to 2. Okay, it's important that you always do less than or equal to the number you've got in the sample when you work out that probability. Okay, or greater than or equal to if you're looking at the upper tail. Compare that probability with significance level. If that probability is greater than the significance level, you accept H0. So if the probability is larger than 5% or larger than 10%, then you're saying there's not enough evidence, so you accept the null hypothesis, you accept what was originally true. You only reject H0 if that probability is less than your significance level. And really important, always write that conclusion and put it in context. Okay, so read the question, look at what it's talking about, look at the scenario, use that in your answer. Now your turn is to have a look at these questions. Also finish off the Lorna question as well. Just make sure that you're doing the starter question as well. I'll talk a little bit about the starter question on Thursday. Mostly looks good from what I can see, but would like a few more people to have a go at that question if you haven't already, and I can make a bit more of a comment about how you're getting on. Make sure you ask for help if you're stuck. Okay, we can just give you hints in the chat. We can do one-to-one calls if you need it. Don't just copy from the work solutions and leave a question blank. Okay, I have seen that. I know yesterday one of the questions was quite difficult. Just ask us if you're not sure about it. Okay, unless any questions, we'll leave it there, and we'll see you on Thursday. Unless you want to get in contact before then, see you on Thursday for the second part of this, which is two-tailed tests. If there's any questions, please let me know. I'm going to stop recording here.